Alright, hell yeah. So no one knows what radians is, and it's kind of just my joke. So I'm going to visually show you kind of what a radian is. So kind of make this. So we have a string, and we're going to measure the radius. Now we're going to do the inside of this circle because this rope will lay in nicely. So booyah, there is 1 radius. And let's confirm that. Does that look like there's the center? Made it kind of a little bit long, but it doesn't really matter. We'll just kind of continue on. And we need 6 of these. You know what I mean? You need 6.28, so we'll actually cut 7 just to kind of maybe show you. But booyah, there's 3. You might want to fast forward because we got a couple more to cut. And I want to get fairly accurate, you know what I mean? So hell yeah, there's the radius, booyah. Alright, how many is that? I think we're getting pretty close. Alright, that's 6. We need 1 more. And we'll put the 7th one off to the side. Alright, hell yeah. So we cut our rope, and now what we're going to do is, you know what I mean, hey, maybe in polar coordinates, your radius goes this direction, and your angle goes up this direction. So what we are measuring is angles. So, so hell yeah. So if we have a line going across, and then we have a line going up this way, hey, look at that angle. And it might not look like 60 degrees, well, because it's not, it's 57.3. But it's pretty close to 60. You know, 45 is going to be, so here's 0, here's 90, 45 is right in between. So hell yeah, it just looks like a little bit more. And you know, I probably didn't cut these 100%, but hell yeah. So now what you're going to do is you're going to, and this is the definition of 1 radian, you know what I mean? And in a circle, there's going to be 2 pi radians or 6.28. So let's show you that we'll do 6 of these radiuses. And still, at the end of the day, we took the radius, we cut a string, and then we're going to drape that string around the circle. So we're going to drape those radiuses. So even though that this is curved, this length is still the length of the radius. So that's pretty wild. Okay, hell yeah. And then, so booyah, we did it 6 times, and, oh man, it should have came out just a little bit. You know what I mean? It's almost 6. I mean, at the end of the day, close enough, you know, it should be 6.28. Like, I should be able to cut this one in half, and then cut it again in a quarter, you know what I mean? And that's 6.25, and I should be able to kind of jam it in here, you know what I mean? So if I did this 100%, well, there you go. So that's 6.28. Alright, hell yeah. And now I'm actually going to make this just a touch longer video because I use this axiom, because still, no one knows what a radius, even though I just did that, still no one knows. So what I do is I draw a circle, draw the radius out here, mark it as radius, and then just visualize it. You know, visualize that you're cutting this string, and then I'm going to drape this string around. Well, if I drape, I'm going to get about to there, and then so do that, and then just realize, oh yeah, no duh, it's about 60. And so, so that's what I do. I take a circle and kind of make it, just divvy it up into 6 segments, and then you're close enough. And then we can say that this is 1 radian because it's 1 radius. And then, but maybe that's not good enough, so I use this axiom, is no one knows what radians are. But they're still just an angle, so you can still use this like angle theta. So let's draw a bigger circle. The radius, we're going to do that, you know, divvied up into 6 little chunks, and then we're still going to call this an angle. And that angle is going to have units of radians, you know, whatever the number is. And right here we have 1, so that angle is 1 radian. Okay, so that's where I come over here and just kind of write down the equations. And how I do this is I say, hey, no one knows what radians are, but radians times radius. If you do this, you get something normal. So just think radians times radius is something normal. And this probably is the harder one. The middle one's a little bit easier. But what we said was that, well, radians times radius, this gives you the arc length. So I should just spell it out. And does that make sense? If I take this degree, its number is 1, and if I multiply this 1 by this this radius, then I get this arc length. Hell yeah, you know what I mean? And And hell yeah, since we did one, that might be like, well, no duh, right? But if we do, you know, how many radians are in a circle? You know what I mean? So we're going to have 6.28. So if you do 6.28 or 2 pi, and then we multiply that by the radius, whatever the radius is, that gives us this whole circumference. Okay, and then we can double check that because, you know, if we go back to 8th grade, like the circumference is pi d, and then you're like, oh, okay, and then d is just kind of 2 times the radius, so I could substitute that. So we get circumference is pi 2r, or typically 2 pi r. That's going to be the circumference, and that's what we get here. We took the radians, 2 pi radians, multiplied it by the radius, and then you get the circumference. So hell yeah. So radians times radius is arc length. The other one that we do is radians per second times radius. This is tangential velocity. Tangential velocity. Hell yeah. Okay, and then I guess the third one, we'll just write it out, is radians per second squared times radius is tangential acceleration. Alright, hell yeah. And then it's kind of good to, what are the symbols on this? Well, the symbol for radian is an angle. Radius is just r. Arc length is s. You know, that's the only maybe weird one. Angular velocity is omega. That's radians per second. So yeah, even though angular velocity, a lot of professors will just keep calling it omega because it's kind of difficult to say radians per second. What am I getting at? Oh yeah, it still has radians in it, so it's radians times radius gives you something normal. It's still kind of a weird term, especially this one. This is angular acceleration. It's radians per second squared. Now radians is dimensionless, so it makes sense that you have to multiply it by some sort of, the radius to actually get units. So this is dimensionless. You multiply it by like radius in meters, and you get an arc length in meters. This has a dimension, but the radians part is dimensionless, but you got 1 divided by seconds multiplied by meters. This gives you meters per second, which would be tangential velocity. Dimensionless, but this does have units of divided by seconds squared times meters, and then you get meters per second squared. Hell yeah, and so that's going to be the dimensions for acceleration. Okay, sweet. But this, I literally do this all the time, just kind of like spell it out and say radians times radius is something normal, and know that there's 3 different things that I can, has radians in it, multiply by the radius, I get that something normal. And then so these equations are the angle times the radius is the arc length, omega times the radius is the tangential velocity, and alpha times the radius is tangential acceleration. But a lot of the times they will call this just alpha and omega because it's difficult to say angular acceleration, angular velocity. You know what I mean? Just because we're so used to just doing normal velocity, normal acceleration. But this is the angular acceleration. You know what I mean? You have to multiply it by the radius to get something kind of useful. All right, and so let's go back to our pi. And yeah, let's kick these out. So we said that if we have one of these, this is the radius, we drape it in a circle. This angle right here is 1 radian. Okay, so you can just imagine if I'm on a circle and I can get up to here, well, I just swept through an angle of 1 radian. And so let's say it takes me 1 second to do this. So I'm going to go 0, 1. Cool, and if I'm going this speed, 0, 1, 2, 3, 4, 5, 6, I'm basically getting around the circle in 6 seconds. So what we're really used to is just revolutions per second. So it looks like I did 1 revolution in 6 seconds. You know what I mean? And even that, we're typically used to things going faster, like maybe 2 revolutions a second, or like 1,000, or, you know, with power tools or something. Or power tools don't go 1,000, they go 100. But anyway, because they go about 1,000 revolutions per minute, you'd have to divide by 60. Anyway, so so I guess what I'm getting at is that we can get the velocity by figuring out what the angle change. So if we have this angle change of 1 radian, we're going to go at an angle of 1 radian per second. You know what I mean? So, and I think we get that. If I said I'm going to turn at an angle of 360 degrees in a second, we all understand that. But the second you actually say radians, it makes littler sense. I was just thinking, because you have 2 pi in a full circle, you know, next time you see a skier that's ready to go off a jump, be like, hey, show me 2 pi. You know what I mean? It'd be like the nerdy version of like, hey, do a kickflip. You know what I mean? Do 2 pi. Anyway, that'd be the same thing as do 360. But that just shows you, no one ever yells 2 pi. You go to the X Games, even in Canada, they're not like, oh, did you see the 2 pi out of that person? You know what I mean? No one says that. You know what I mean? So even though, like, Canadians and Europeans have the metric, and the rest of the world has the metric, but still, everyone still uses, you know, when you go to the X Games in all those countries, you're like, hey, that was a cool 900, you know, 1200. It's all in degrees. 360 degrees is a circle. No one does, you know, 2 pi radians. But hell yeah. And then even the fact that it's in 2 pi, that's not even a number, it feels like. You know what I mean? It's just kind of like a symbolic, you know, something you would worship. But it's at the end of the day, it's 6.28, but really, at the end of the day, it's 6. So you're going 6 radians. So if you actually do a full circle in a second, you're going 6 radians per second. We're going to go back to our example. We're going to go through this angle in 1 second. So we're going to go 1 radian per second. Hell yeah. And what we did right there is we just found the angular speed. You know what I mean? So in this 1 second, we got to there. And what's the units on angular speed? It's radians per second, and we're doing 1 of those. So 1 radian per second. But what's our tangential velocity? Like, what are we actually traveling? Well, I mean, we know we're going to get around this circle in 6 seconds. But maybe we want to know how big this circle is. Alright, hell yeah. So we want to measure the radius. Looks like the radius is 3.5 inches. So cool. In 1 second, we're actually going up to this degree, but we're going 3.5 inches. So our velocity is 3.5 inches per second. Alright, hell yeah. And now let's say... Alright, the easiest way to do angular acceleration is like, well, let's say we're at a dead stop, but we are going to accelerate. In 1 second, we're going to accelerate to 1 radian per second. So this is kind of a stumper, but it's just good to get kind of visually affluent with acceleration. If I'm going to, if my angular speed is going to go from, like right now I'm not moving. I'm going to go 0 angles per second. But in 1 second, I'm going to be going so the angular acceleration is going to be 1 radian per second squared. And what we say is that this is going to be a change in our angular speed for a change in time. So and again, the units on this are radians per second squared. I wouldn't write it like this. I would say it's 1 radian per second. So we're actually increasing. We're going to have an increase of 1 radian per second, and then do this, per second. And I don't throw another 1 on, but you could. You could do radians per second divided by 1 second. And this is basically going to be your change in radians for your change in time. Hell yeah. Alright, hell yeah, we gotta finish this video, but I'm probably gonna mess up this last part, because it's just angular acceleration. It's kind of difficult, you know what I mean, because I think doing linear velocity is just a lot. Velocity in one dimension, or velocity and acceleration. So if I'm gonna drop a rock off a cliff, it's got a velocity of 0. Now it is going to change in speed, because the acceleration is, let's say, 10 meters per second. See how we written it like this? So this means that in 1 second, I don't know its distance yet, but I do know at this point after, so this is time is equal to 0, time is equal to 1 second, I do know what the velocity is. It's going to be going 10 meters per second. Just like in this case, if I say the angular speed is 0, but I know my acceleration is going to be, in 1 second, is going to be 1 radian per second. So I don't know where it's going to be, but I do know at that location, we're just going to right here, it's going to have an angular speed of 1 radian per second. So right here it had an angular speed times 0 times 1. This had 0 radians per second. Okay, so now let's go back to our linear velocity. So what do we know about this? We know that, because if I want to find distance, if I'm driving in a car, I'd be like, hey, if I drove from this town to this town, I was going 60 miles per hour. And I drove, and I drove for 1 hour. So how far did I drive? Looks like I drove 60 miles. I think we all kind of get that reference. But this is where you have to be kind of creative. I'm going to drive for an hour, and I'm going to start at 0 miles per hour, and I'm going to slowly increase my speed to 60 miles per hour. So, I would kind of do this as for my velocity. So we have 60 here and 0 here, and then so we have to get an average velocity. So you can do that, or velocity average, and my average velocity would be 30 miles per hour, and I drove for an hour. So sweet. Sorry about that. Velocity should be over here. But hell yeah. So I'm just going to go 30 miles. So the same thing happens here. I'm not going 0 miles per hour. But I'm also not going 10. These are just the starting and then the finishing speed. So I start at 0, get up here to like 10. So I do have to find an average. So the velocity average is just the difference. It's kind of the halfway point between them. All right, hell yeah. And so that's going to be 5 meters per second. So in that 1 second, I'm traveling 5 meters per second. So I'm traveling a speed of 5 meters per second for 1 second. Looks like I traveled 5 meters. Just like it's very easy to see that, hey, if I'm traveling an average speed of 30 miles per hour for 1 hour, traveled 30 miles. Okay, hell yeah, let's finish this off and then do the acceleration. So if at some point I'm going to have a speed of 1 radian per second, but I started at 0 radians per second, my average, so omega average, is going to be 0.5 radians per second. So that's basically, in this 1 second, I'm traveling at an average speed of 0.5 radians per second. Here is a radian, and so I'm just traveling half that. So my average speed, but this, I'm not traveling like this speed. I'm not going from 0 to here. That's just my average speed. Like right here, I'm actually, oh shoot, I'm gonna mess this up. No, this is good. Let's forge on, because yeah, and we'll do another iteration. Because if I do another iteration on here at time is equal to 2 seconds, I'm going to go from 10 meters per second. Now my velocity right here is 20 meters per second, because I increased my velocity. Let's quickly go over here. My omega at 2 seconds is going to be 2 radians per second. So the average between 1 and 2. Now my average is 1.5 radians per second. So in this first second, hell yeah. On average, I'm going at an average speed of 0.5 radians in a second, so I get to here. And then in the next second, I'm going to go 1.5. So here's 1 and here's a half. So in the next second, I'm going to be going, so it's going to be 0, 1, 0, 2. So we have like 1, 2. So I'm increasing my speed. Now the thing that this points out, and we'll do this maybe one more time, is I'm not going like this speed and then all of a sudden like increasing my speed, and then all of a sudden here increasing my speed. It's going to be continuous. So if I'm going here at a slow stop, I'm going to go 0, 1, 2. So it's just a nice increase in speed. So your change in speed is always nice and smooth. That would be angular acceleration. Just because angular acceleration is, you're constantly accelerating around. But yeah, let's do it one more time without this linear, because we're kind of getting the hang of this. At 3 seconds, I'm going to be going at 3 radians per second with an average of, what's the average between 2 and 3? It's going to be 2.5 radians per second. So, so in the first second, in the second second, and now we're going to go 2, 1, 2, and I don't mind cutting these up. This is kind of fascinating. Hell yeah. So we got 2.5. So 0, 1, and let's even chop this one up so you kind of see that break. Yeah, because in that first second, we're just going to go that half. Hell yeah. So, and yeah, let's even mark the seconds. So, time 1 second, time 2 seconds, and then hell yeah, time 3 seconds. So we're going to go 0, 1, 0, 2, 0, 3. 0, 1, 0, 2, 0, 3. So, 1, 2, 3. So if I count 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, or like it's hard to count, 0, 1, 2, yeah, anyway. So, but yeah, we are slowly, we're increasing our speed around here. And at that accelerate, we're just going to be keeping increasing our speed until something changes. Alright, so that goes over what radians are, what angular speed is, and then even angular, see, it's even really hard to say, angular acceleration. And it's really cool how it's very similar to velocity and acceleration in one direction, and how these equations, can be synonymous. But I think I'm going to end it there. Thanks for joining me on this one, and hell yeah.